Good morning all. Today's video lecture is on the topic NMR spectroscopy or nuclear magnetic resonance spectroscopy. The most dedicated application of NMR is MRI scanning, magnetic resonance imaging. Okay. In NMR spectroscopy, we use radio frequency radiation. And the NMR instrument is having a very powerful magnet. So when a molecule is to be analyzed, is kept in a magnetic field, radio frequency radiation induce transition between magnetic energy levels of the nuclei, resulting in generation of respective NMR spectrum. Okay, so NMR spectroscopy is the interaction of magnetic field of radio waves with the magnetic field of atoms having non-zero spin. So atoms having non-zero spin are active in only those atoms having non-zero spin are active in NMR. Only those atoms give NMR spectra. Okay. So the essential condition for a compound to be NMR active is there should be the value of spin quantum number I should be greater than 0. So what all nuclei are active in NMR? Hydrogen, represented as 1H, C13, N15, P31, F19. All these atoms having spin quantum number I greater than 0. Therefore, all these atoms are active in NMR. Of all these, the most widely used NMR technique is, most widely developed technique is proton NMR or hydrogen NMR and C13 NMR. So our syllabus include proton NMR spectroscopy. Or hydrogen NMR spectroscopy. Hydrogen possesses only one proton and there is no neutrons in hydrogen. Therefore, hydrogen spectroscopy is also called as proton NMR spectroscopy. Hydrogen is considered as a proton. Then the spin quantum number value I of hydrogen is half. Proton NMR spectroscopy means hydrogen or a proton, or this is equivalent to the nucleus. Nucleus of hydrogen contain one proton having positive charge. So what is the charge of the nucleus? Nucleus is positively charged for proton. So since nucleus is having a positive charge, it spins on its own axis and it generates a magnetic field. We can consider nucleus of proton as a tiny bar magnet. So it is having a magnetic field and these hydrogen atoms having spin is randomly oriented in space. So when this proton is placed in a powerful magnetic field having field strength B0, all these protons are aligned either with the field. We give a very powerful magnetic field having strength B0. So all these protons align either with the field or against the field. Just like this, protons are aligned either with the field or against the field. There are two orientations in the case of proton and that can be decided by the equation. If the value of spin quantum number is I, number of orientations is equal to 2i plus 1. For proton, the value of I is half, therefore 2 into half plus 1 is equal to 2. So for proton, there are two orientations. Okay. In the absence of magnetic field, all the proton which act as a tiny bar magnet are randomly oriented, and if when placed in a magnetic field, these orientations are divided into two, alpha or beta state, or minus half or plus half state. This is a low energy, this is energy, this is a low energy state, this is a high energy state, having delta E value. Delta E is equal to h nu. So this band width is proportional to the frequency nu. Okay. So as the magnetic field strength changes, the frequency also changes. When the sample having a large number of proton is placed in the powerful magnet of the NMR instrument, based on the magnetic field, the sample, the orientations are split into two, plus half and minus half, having energy change delta E is equal to h nu. This is in the absence of field, no field. Here a magnetic field strength is given. Okay, and the instrument possesses radio frequency radiation. So the radio waves are given to the sample. Instrument is having a particular frequency that is constant for a particular instrument. So instrument is having a frequency of the radio waves is given to the sample, and we give an increasing magnetic field. We give an increasing magnetic field. Instrument is having a frequency nu. Here this is a frequency of the sample, and by increasing the magnetic field, this frequency varies, and when this frequency of the sample is equivalent to the frequency of the radio frequency radiation, there is resonance, and we get NMR spectra, peak in the NMR instrument. Okay, so the frequency of the sample is called as precessional frequency. That can be varied by changing the magnetic field of the instrument. So instrument is having the arrangement of increasing its magnetic field. So by increasing or changing the magnetic field, the energy, the precessional frequency, delta is equal to h nu. This is precessional frequency that can be changed by changing the magnetic field. And when this frequency, the precessional frequency, matches with the frequency of the instrument, that is constant for a particular instrument, when these are equivalent to each other, then we can say the term there is resonance. This nuclear magnetic resonance spectroscopy means here we are studying nucleus, therefore the term nucleus is there, nuclear is there, then very powerful magnetic field strength is given. That is why there is a term magnetic, nuclear magnetic. Then what is resonance? Here when these when there is resonance, that is when the frequency of the precessional frequency of the sample is identical with the frequency of the instrument, then only there is resonance. Instrument is having a constant frequency, but the frequency of the sample, the precessional frequency of the sample varies. How it varies? It varies by changing the magnetic field strength of the instrument. Okay, thus this is a principle of NMR spectroscopy, and when this frequency matches when the precessional frequency is equivalent to the frequency of the instrument, there is flipping of proton from this low energy state to the high energy state. And this flipping result in the formation of a signal in the NMR spectra. Okay. When the precessional frequency matches with the frequency of the instrument is having a particular radio frequency, radio waves are used in the instrument. When these two frequencies matches with each other, there is flipping of proton from the low energy state to the high energy state, and the flipping result in the formation of generation of signal in the NMR spectra. Number of peaks in the NMR spectra means these are the number of, there are 3 peaks in the NMR spectra. This is NMR spectra, that means there are 3 different set of protons. For example, you know the formula of ethanol, CH3 CH2OH. How many peaks are there in the NMR spectra of ethanol? Ethanol contains 3 set of proton. CH3 proton is different from CH2 proton in the NMR spectra. Similarly, these two are different from the OH proton. Only protons give signal in the NMR spectra. Number of peaks in NMR spectra is equivalent to number of different sets of protons. This is very important. Number of peaks in the NMR spectra. Here there are 3 peaks. 1, 2, 3. 3 peaks means the sample contains 3 different set of protons. So in ethanol, CH3 is a particular set of proton that is different from CH2 in the NMR spectra. Again, the OH proton is again different in the NMR spectra. Therefore, the sample contains 3 different set of protons, and therefore we can expect 3 peaks in the NMR spectra of ethanol. Similarly, consider another compound, CH3 CH2Cl, chloroethane. Okay, how many peaks can we expect in the NMR spectra of chloroethane? Okay, the compound contain 2 different set of protons. What are they? CH3 proton and CH2 proton. Cl doesn't give peak in the NMR spectra because we study the proton NMR spectroscopy. We can count only hydrogen. We get peak corresponding to the different set of hydrogens or protons. So CH3 proton is different from CH2 proton. Therefore, we get 2 peaks in the NMR spectra of chloroethane. Similarly, let's see another example. CH3 CH2 CH3. Okay, so for this compound, how many different set of protons are there in CH3 CH2 CH3? This CH3 is equivalent to this CH3. So corresponding to these two CH3 groups, we get only 1 peak, and CH2 is different, therefore another peak is obtained. Therefore, there are 2 peaks in the NMR spectra of this compound, that is propane. Okay, so from the number of peaks in the NMR spectra, we can predict the number of different set of protons present in a compound. Another example is acetone, CH3 CO CH3. And what about acetone? How many peaks we expect in the case of acetone? Acetone contains 3 carbon atoms. So this CH3 is identical with this CH3, both are same. Corresponding to 2 CH3 groups, we get only 1 peak, and that middle carbon doesn't possess any number of proton. Therefore, no signal for this CO group. No signal. So how many peaks in the NMR spectra of acetone? We get only 1 peak corresponding to the 2 CH3 groups. Now consider the compound Okay, pentene. Okay, 2,2-dimethyl propane, or UPC can be name can be written. Okay, whatever, consider this compound. And what about the NMR spectra of this compound? So the NMR spectra of the compound give only a single intense peak. What is the reason? The compound contain CH3 group only. The CH3 is identical with this one. All the 4 CH3 groups are identical. The middle carbon doesn't possess any number of protons. Therefore, we get a single peak corresponding to the 4 CH3 groups in the NMR spectra of this compound. And another example is chloropropane. CH3, CH2, CH2, Cl. So how many peaks in the NMR spectra of chloropropane? Number of peaks is equivalent to the number of different set of protons. Okay, so here we have one CH3 group. Yes, this is CH3 group, and we have two CH2 groups, CH2 and CH2. Okay, if these two CH2 groups are identical, but the difference is we get one peak corresponding to the CH3 group, we get one peak. And what about the two CH2? The second CH2 is attached to an electronegative atom, chlorine. Therefore, the chemical environment of these two CH2 are different. The chemical environment of this CH2 is different from the chemical environment of the second CH2. Therefore, we get two peaks corresponding to the two CH2 groups. Okay. In the case of CH3, CH2, CH2, CH3, this compound, we get only two peaks corresponding to CH3 and CH2, because the two CH2 groups have the same chemical environment. The two CH3 groups have the same chemical environment. Corresponding to the two CH3, we get single peak, and corresponding to the two CH2, we get single peak. Therefore, two peaks in the NMR spectra of this compound butane. But for this compound chloropropane, the two CH2 groups are having different chemical environment. The reason is the second CH2 is attached with an electronegative atom, and so the chemical environment of the two CH2 are different, and we get two peaks corresponding to the two CH2 groups. So the number of peaks in the NMR spectra of CH3, CH2, CH2, Cl is 3. Okay. So thus, by taking the NMR spectra of a compound, we can very easily identify the number of different set of protons in a compound. Okay, so number of peaks is equivalent to the number of different set of protons. Thus, NMR spectroscopy or NMR spectra is a very, very powerful tool for the qualitative analysis or the structure elucidation of organic compounds. Thank you.